Welcome aviators, and thank you for joining us for Aerodynamic Forces. So today we will be talking about the four forces of flight, and also we'll be talking about Bernoulli's principle. So let's start off with talking about the four forces of flight. What are they exactly? If we look in Ecclesiastes 1:9, we will see that which has been done is what will be, that which is done is what will be done, and there is nothing new under the sun. When we look at this next clip, it definitely shows there is nothing new under the sun.
When an airplane is flying horizontally at a constant velocity, the forces acting upon it are in equilibrium. The retarding force, or drag, equals the propelling force, or thrust. The lift must equal the total weight of the airplane. Therefore, the lift and drag equations serve to determine how much weight an airfoil will lift under certain conditions and how much thrust horsepower is required to overcome the total drag of the airplane.
Oh, sorry. Now at the beginning of our video, we mentioned that we're not just going to talk about the four forces of flight, we also talked about touching on Bernoulli's principle for just a moment. Now what Bernoulli would do is these experiments with gases and fluids to see what would happen under certain conditions. The one that we use the most has to do with forcing the gas or fluid through a tube, have it go to a constricted point, and then have it go back out the other side to the same diameter tube as what it entered. And the results were very interesting. If there was a constant velocity and pressure on one side of the tube, when it got to that constricted point, the velocity would increase, but the pressure would decrease. But then after getting past that point of constriction, then the velocity would return back to its original state, and so would the pressure. That's just cool! Literally, because with the decrease of pressure, there's also going to be a decrease in temperature. But that's a subject we'll touch on later. Now, if we take that tube and we were to take the top part off of it, we'd still have a lower section that would have a curved spot that, when we look at it closely, resembles the shape of our wing. By using this shape, airflow going over the top of it is still developing that low pressure. This low pressure, wanting to mix with the higher pressure above it, is what develops a portion of our lift. Now there are other variables in developing the lift, such as a high pressure below the wing as well, but the majority of the lift is developed by the low pressure on top of the wing. I will be focusing on this principle for the main portion of the developed lift of an airplane as it pertains to the FAA testing. Now it's one thing to talk about the theory, but it's another to put it to the test. So if you look here, I have my leaf blower, and I'm blowing air over just one of the curved sides of the tube. An interesting thing happens. You'll see that it actually pulls it along that side versus blowing it away. So does this really make sense that it would actually suck it along when I'm blowing pressure over the top of it? Well, by Bernoulli's principle, it makes total sense. By forcing the airflow over the curved surface of the tube, I'm creating a low pressure and it's dragging that tube. Now here's another view that we can look at just to show that it can develop lift. Now putting the tube over on its side to give a different illustration, basically the same principles are applied here. I force the air over the top of the curved portion of the tube and it allows it to bounce up or lift. And if I could hold the leaf blower steady enough, it will actually hold it in flight right off the table. Now, if you notice, when I point the leaf blower to the bottom of the tube, it doesn't make it jump up. If anything, it makes it seat down to the table a little bit stronger.